This is no ordinary TV receiver. As well as being able to receive pictures, it can also receive broadcast information services. Let me show you. I'll switch to text, and you can immediately see that we now have a static page of information. This is a system being broadcast by the BBC, which is called CFAX, and there's a similar system being broadcast by the independent television companies. I'll show you that by erasing this, switching channels on this set. I'll dial a new page number, and we'll have to wait a moment or two for the next page number to come round. I've selected, in fact, page number 100. You'll see it in a moment. Well, this is it. As you can see, it's called Oracle. And just like the page we were just looking at, it's an index page. It tells us other page numbers where we can get information about various things. The format is that we can have up to 24 rows of characters, and in each row we can have up to 40 characters. So that's the format of the system. Now, the question that arises is, how is this transmitted along with the television picture? Well, let me show you. I'll switch that off, and I'll switch back to our picture, and I'll ask Gaby to adjust the frame sync on the receiver so that the receiver is now out of synchronization. This is so that I can show you the gap between one field and the next field. Now, in that gap we have the field synchronization pulse, which lies in this region. Following that, a number of blank lines, and then, as you can see, a number of dots dancing about. Now, that is a digital stream of information which is giving us the information in the CFAX system. Well, in addition to these two broadcast systems I've talked about, CFAX and Oracle, there's also a post office system which we can see on another receiver. And this system is called View Data. You can see the sort of display there. It's a very similar format to the one we've been talking about. And we'll be saying more about that later in the program. But for the first part of the program, we're going to concentrate on the broadcast teletext systems. So first of all, I'm going to look back at that CFAX index page. So if I switch back to text and dial up 200, there's our CFAX page. Now, first thing you notice, or at least I'd like to draw to your attention, is a page number here which is continually changing. And that tells us at any moment which page is actually being transmitted. But as you can see, we can capture a page and leave it on the screen. Now, one of the pages mentioned on here is Open University, page 280. So I'm going to dial that up simply to show you how easy it is to access a page. And I was lucky that time because 280 was just about to be broadcast as I dialed it up. And there's our page. In addition to the characters I was talking about before, we can also send graphic symbols which can do things like forming this strange U for the Open University symbol. Well, having talked a bit about the two systems that are available, I'm going to ask Gaby to explain in more detail how we generate the characters on the screen.
As David said, the CFAX picture has up to 24 rows. We call them rows so as to keep the word lines for the raster lines which are scanned by the electron beam. This avoids confusion.
When Mary left
Dots on a 7 by 5. Seven lines of these 5 dots go to make up a complete character. The text is transmitted in digital form. The information for the page we have selected is stored in a memory in the receiver. Each character is stored as a 7-bit word. The video signal needed to produce the dots is obtained from a circuit called a character generator. When the picture is built up, each 7-bit word is taken out of the memory in turn. If, for instance, capital A is the next character we want to produce, then we have the digital signal 1, 0, 0, 0, 0, 0, 1, which represents capital A. And this produces the appropriate video signal to produce capital A on the screen. In some simple receivers, the same pattern is produced for odd and even fields. So because of the interlace, we get each line repeated in pairs. characters like this can sometimes be difficult to read. So to improve legibility, some character generators introduce differences between the two fields so as to smooth out the diagonals. This is known as character rounding. I can demonstrate character rounding with a special receiver, a research receiver, which enables me to switch the rounding in and out. I can do this by operating this switch. And as I do it, you should be able to see what's happening to those characters which have got diagonals like A's and X's, with rounding, without rounding. So that is the feature of character rounding which makes things more legible. Now, another feature is the possibility of having characters in different colors. Turning characters into color is done with special control characters. For instance, the word 24 rows is in purple. Now, with my special receiver, I can reveal the control characters. Here they are, coming on and off. Now, this character is saying everything after the character should be in purple. And this character is saying everything after that should be white, so we revert to white. Now, in an ordinary receiver, the control characters don't show. We simply have spaces, and we have to have a space before each control character. Now, this is a slight snag. We could avoid it by having, for the 6 colors plus white available, by having 7 different A's, 7 different B's, and so on. We need 7 times the number of characters, and this would require more bits per character, in fact 3 more bits per character, and this would mean that the data took a lot longer to be sent. So in designing the system, it was decided that it would be more effective to put up with having a gap whenever there was a control signal, rather than to reduce the data rate. Now, special control signals can also be used for other purposes. They can be used to produce graphic symbols like these. They consist, essentially, instead of having a 7 by 5 matrix of dots, there is a set of 6 rectangles, which can be either black or white. And by having the appropriate control character, we can go over to these and build up any graphics by appropriate combinations of these black and white rectangles. For instance, if we look at our special OU picture, the U, this limb of the U, is made up of these characters, and I can show you the control characters. These control characters are saying, go over to graphics. So that when these characters are sent, what follows is graphics, and the whole thing is built up out of graphics. So these are some of the main features of teletext displays. The next thing we need to know is how the 7-bit data signal can reach the teletext decoder. This is where broadcast and telephone link systems differ. David will start off by looking at a broadcast system.
Well, these are the teletext dots that you saw before, lying in this region, in the interval just after the field synchronization pulse, which comes at about this level. Now, in fact, we're using 4 lines of the television picture. 2 lines in the odd field, numbers 17 and 18, and 2 lines in the even field, numbers 330 and 331. Now, if we look at the system diagram for a teletext receiver, you can see how this fits into the system. Now, the front end of the receiver, that is the tuner, and the IF amplifier, right up to the video detector, are standard, as for a standard receiver. And in fact, with the switch in the upper position on the top row of the diagram there, you can see that the output of the video detector goes straight to the video amplifier and to the cathode ray tube in the normal way. But when the switch is down, we select an output from the teletext decoder. Now, the decoder is fed with the video signal, but it extracts just the digital data stream represented by the dots we've just been looking at. And there's also an input from the sync separator to make the decoder work correctly. So the teletext output goes to the video amplifier, and now it's fed, the video amplifier is fed with characters from the character generator, and we display the teletext information. Now, what does the actual waveform of the dots look like? Well, if we look at the oscilloscope screen now, you can see a few lines of the TV picture. Now, these are lines in the area of the dots where we were just looking on the picture. The first 2 lines on the left-hand side of the screen are blank lines, and the next line contains some transmitter control pulses, so we're not concerned with those. The next two lines look similar, and you can see that they have rapidly changing sets of pulses. These are the teletext data on two adjacent lines of one of the fields of the picture. The next line, in fact, has got various test signals, pulse and bar, and a grayscale. And then there's a colour test signal on the next one. So we don't need to look at those. If we look back at the centre, those two middle groups of pulses are the teletext data. Now, this next picture shows us what these pulses look like just after the synchronization pulse at the beginning of the line. There's a series of pulses which are called the clock run-in, which run at a regular rate, and they're then followed by a framing code, and then following that we then start to get a random collection of pulses determined by the particular sort of data we're trying to send. Now, all that lot has to be fitted into a line, and that determines the data rate of the system. So to see how this all comes about, let's look at the waveform of a line. Now, this represents the waveform of one of the lines, separated by the two synchronization pulses, the line sync pulses, which are the negative going pulses. And you can see a little squiggle just after the first sync pulse, which represents the color subcarrier, which you'll learn about in a later unit. Now, the interval we need to leave, out of the total 64 microseconds we have for the line repetition period, we need to leave 12 microseconds out of that, and that leaves us with 52 microseconds in which to send the digital data. Now, the way the system is arranged is that for each of the television lines, we send enough data to fill one of the rows on the displayed teletext picture. And there are 40 characters in a row, and for each character there are 7 bits. And in addition to that, there's also a parity bit with each character, so it makes 8 bits per character. So that means that we get 40 characters times 8 bits, 320 bits for a row of information on the screen. In addition to that, we also have 40 bits for synchronization and framing, so that makes a total of 360 bits, which have to be fitted into the 52 microseconds. Now, that means that the bit rate that, as a result, is 6.923 megabits per second. Now, that's the very least bit rate that we could get away with. In fact, a bit rate slightly higher than that is chosen, 6.9375, which happens to be an integral of the line frequency, and it's convenient that it's an integral. That's why it's chosen to be that way. Well, now that we've seen how the system consideration determines the bit rate, which is getting on for 7 megabits per second, Gaby is going to discuss how that manages to fit into the bandwidth available in the television system.
The signal which is used was chosen to allow a maximum data rate within the available bandwidth. A non-return to zero code is used for the binary digital signals. The level does not change for consecutive ones or for consecutive zeros, only for transitions between zeros and ones, or for transitions between ones and zeros. If a return to zero pulse is chosen, it looks like this. We get a transition for each bit. Now, in order to send a return to zero pulse, we would need at least this frequency. Now, in the case of the non-return to zero, we need to consider a worst-case signal consisting of consecutive ones and zeros. In order to transmit this signal, we need at least to transmit the fundamental frequency, which is a sine wave shown. Now, the two signals have got as many bits in a given time, but the non-return to zero signal has a fundamental frequency, in this case, which is half the frequency we needed for the return to zero signal. So in order to send signals at a given rate with non-return to zero, we require half the bandwidth we would with a return to zero signal. And this is why non-return to zero signals are chosen. Of course, we don't use square waves as our pulse shape, because that would require far too many Fourier components. We use essentially a sinusoid, but a sinusoid goes alternatively positive and negative. And of course, a television signal can only be of one polarity. The signal has to be between blanking level and peak white level. So in order to get around this difficulty, we use what is known as a raised cosine signal, which is effectively a sinusoid with a DC level added. So the pulses looked rather like sinusoids, but with an extra DC stuck on. Now, the digital signal, which is carrying the information, is transmitted over the 5.5 megahertz bandwidth, which is available for a standard television channel. But the actual picture which is produced and the video signal for it requires a far greater bandwidth. We can get this because the teletext picture is made up of a limited set of characters. And we know in advance what these characters are. The details of them are stored in the character generator. The 7-bit signals which call for these characters require far less information and therefore less bandwidth than the picture itself. I can demonstrate this by showing the spectra of ordinary pictures and teletext pictures. I have already stored in the spectrum analyzer the spectrum of a standard test card. The scale of the spectrum analyzer is in megahertz, and it goes from 0 to 10 megahertz. This is the spectrum, and it's falling off at about 5.5 megahertz. This peak here represents the color information. You'll be reading about that in the next unit. This is the color subcarrier and color information around here. But the whole spectrum drops off around 5.5 megahertz, and there's very little information beyond there. Now, I'll now look at the signal corresponding to the teletext picture. I'll store that signal. And now we can compare the two. I'll return to the test card. What I've done is to arrange for the lower frequency levels of the two signals to be roughly the same, so we can compare the signals. Now let's have a look at the teletext. Well, with the teletext signal, as you can see, it extends right on, in fact, beyond the 10 megahertz. So we have got a video signal. What we were looking at was the video signal which is being fed to the tube in order to produce a picture. This signal occupies a much wider bandwidth than the 5.5 megahertz, and that is because, of course, we know what kind of signals are involved, and the character generator produces a video signal of a much broader bandwidth than the actual video signal which is transmitted. Now this means that the teletext picture is a much better definition than transmitted broadcast television pictures. So if you look at a teletext picture in the studio and try and see the whole picture, you probably won't be able to read the words because there's far more detail. The detail I can see is far greater than the detail you can see in the studio. So what we're going to do is to take a close-up of one of the characters on the monitor in the studio so that you can see what the information looks like. This is a close-up just of the word CFAX on the picture. And as you can see, it's pretty sharp. But what happens if we were to pass the signal through a band-limiting filter of the type encountered in normal television broadcast? Well, we can do this, and this is a signal which has been through such a filter. You can compare the two. The letters are the same size, but as you can see, having gone through the filter, the signal is very much less clear. So we have very much greater definition on CFAX, and we can see very much more characters. That's why we've got 24 rows of 40 characters. We couldn't possibly send that over the air. But because of digital coding, we can do this. Of course, there's a penalty in using digital coding. If we get one bit wrong, then we get the wrong character, not just a slightly different character. So it's important to have error detection and correction in the system. David mentioned parity bits for each character. That's one way in which we can check for errors by using parity checks. But for more important data, for instance, the framing information, there is a Hamming code to protect that kind of information, and errors can be detected, but they can also be corrected by using the Hamming code. Well, now we've seen some of the features of broadcast teletext. David will look at the wired system developed by the post office. This is called view data.
Well, this is the view data display that we saw before. It's a fairly normal TV set, except that it has the decoder for view data. In addition, we have a post office modem that I mentioned before, a telephone line, and also a keyboard, which is one way of putting information into the system to ask for pages. Alternatively, in this particular case, I have an ultrasonic control box, which does the same job. Now, on the screen it says 3 for magazine 3, so I'm going to press key 3, which gives me magazine 3. And listed on there under 5 is education, so I'll choose 5. That will give us education. 0 on there's courses available, so I'll try 0 for courses available. I'll dial 0 again for children playgroups. There we go, and now there's different boroughs in the Greater London area. I'll try 0 for Barking. And at the end of this page it says key pound to continue, so I'll do that, and we get another a continuation of the same page effectively. Well, you can see from that how it is that I can access quite detailed information in the system by going down a tree which is summarized in this diagram. This represents the first page with several choices, and then the next page with a number of choices, and the next page, and so on. So you can see that there are different levels in the system. And in fact there are 6 levels, which means that if there were a choice of 10 at each level, we could access 10 to the 6th or a million pages. In principle, there aren't in fact a million pages in the system. Well, having seen that, let's look at the system diagram to see exactly how the bits are connected together. On the left of the diagram, you can see it says that I can fairly quickly access a particular page, and particularly if I remember the number, I can dial it up fairly quickly and access the page almost instantly, and it's then read out in a time around about 7 seconds. On the other hand, the broadcast systems, being broadcast all the time, we have to wait for the particular page we want, and we may or may not be lucky. It just depends when we ask for the page.
Well, he's not going to get down, is he? Well, not down where he should be. Oh, and Gullia's got the Soviet Union a faller and a bad one.